All right, good morning, everybody. So I think last time we started talking about power series and how to build up the series expansion for some basic functions. I mean, we started with the basic power series expansion using geometric series, noting that the sum of a times r to the power n equal to a over 1 minus r, provided the magnitude of the common ratio r is less than 1. So if we just replace x, if we simply replace r by x and use a equals 1, then we'll get the series expansion for 1 over 1 minus x and use that in order to get this expansion. All right. Yeah, sure. And perhaps I can use Kevin's question as a review for this one, right? So let's see. Okay. Though we started doing a similar thing last time to it. Let's see. Mhm. I'll try a similar one to this. Let me see the problem number. Let's try this as problem 6. Um, Find the series expansion for, say, let's see. Let's try 3 over 1 minus 3x, which is a silly modification of what Kevin submitted. But this is fine. You can just modify the numbers so that you can see what would be the series expansion for your case in the homework, I guess. So I just don't want to answer the exact problem from the homework, but this one will be similar. So you just need to follow the process so you get used to it. So remember, our form is a over 1 minus r. This is the form that we are looking for. So that means that here, in this particular case, we can have a is equal to 3 and r is equal to okay, let me make this a plus just to make it more interesting and more aligned to Kevin's question. So before so a is still equal to 3, but finding r is not straightforward, but it's not that hard. Remember, we are required to have a 1 followed by a minus sign, then the common ratio r. So what I'll do is to write it as, 3 over 1 minus negative 3x, right? When you simplify the denominator, you'll get this back, right? But I prefer using this form because that's what the formula calls for. I need to have an a over 1 minus r. So in this case, I can see r to be equal to negative 3x, right? And I can use the expansion. Remember, when expanded, a over 1 minus r is the sum of ar to the n going from 0 to infinity. So this guy that we have can be written as the sum from 0 to infinity of what? A, we already knew a was equal to 3, times r to the power n. But here our r was identified to be minus 3x raised to the power n. So this is the series expansion. Now I can further manipulate this and simplify via playing with loss of exponents. I have here negative 3 times x, both raised to the power n. So I can separate them and write it as negative 3 to the power n, x to the, right? Or actually, I can further write this as 3 times negative 1 to the power n times 3 to the power n times x to the power n. All right. So that I'll have this form. I have negative 1 to the power n, that's the alternating part. And then 3 to the power n times 3 will give me 3 to the power n plus 1 times x to the n. So this would be your series expansion for f of x, 3 over 1 plus 3x. And this is true for all x's, or for all for all x's such that the magnitude of r, but remember our r is negative 3x is less than 1, right? Or basically the absolute value of x is less than 1/3. So as long as your x has magnitude less than 1/3, then you can use this series expansion. All right. Okay, are there any questions with what we did so far? Everything clear? All right. Then if that's the case, then let's proceed to question B. For question B, or the follow-up question, so let's have it part A and then part B. Let g of x be equal to ln of 1 plus 3x. Then find the series expansion for g, right? Now, I can take advantage of the expansion we got for 1 over 1 plus 3x. So recall from part A that 3 over 1 plus 3x has the series expansion negative 1 to the power n, 3 to the power n plus 1, x to the power n, and goes from 0 to infinity for all x's whose magnitude is less than 1/3, right? So I need to find a relationship between this and this guy so that I know what to do with the series expansion to obtain a new series representation for the function g, right? So I have here a rational function and I have an ln. And remember that they are related via integration. So here you should note that the integral of 3 over 1 plus 3x dx can be obtained by letting u to be equal to 1 plus 3x. Du would then be 3 dx. And luckily, that is present here. So this guy is just du over u. So this is ln of the absolute value of u plus c. And this guy would be ln of the absolute value of 1 plus 3x plus c. And note that here we found out that the given function, right, is the integral of the function we have for part A, right? So now this is what we have. We know that ln of 1 plus 3x, but this would be for all x's whose magnitude is less than 1/3. Since the magnitude of x is less than 1/3, I'm sure that 1 plus 3x will always be positive. So that's why I got rid of the absolute value bars here, which I wanted because that's the given function g, right? So we know that this is equal to the integral of 3 over 1 plus 3x dx. But the thing is, we all know from part A that this guy has a series representation. So I can write it as negative 1 to the power n, 3 to the power n plus 1 times x to the power n, and going from 0 to positive infinity, dx from our answer in part A. So all I did here is to replace this guy with the series expansion we obtained from part A. Okay? And we know that this guy, the series, will absolutely converge for all x's less than 1/3. And the beauty about absolutely convergent series is that we can interchange the order of the integral and the summation. So instead of integrating an infinite series of integrals, so what I can do here is this. Oops. I can put the summation for later and do the integration first. all right? Which is fine because the thing inside the integral is a polynomial, right? So, and we are integrating with respect to x. So all those without an x are treated as constants. So these guys can go out of the integral. So I'll have a -1 to the power n, 3 to the power n plus 1, and we'll be left with the integral of x to the n. But for that, I can just use the power rule for integrals. The integral of x to the power n, you should remember, is x to the power n plus 1 all over n plus 1 plus an arbitrary constant all the way out of the summation. All right. Now the last step is to find a value of c for this expansion, because what we have here is this. So far, we know that ln of 1 plus 3x is equal to this summation over here. But what's left to be done is to determine the value of c. Now to find the value of c, we want to choose x equals 0, and you will see why. When x is equal to 0, then we'll have ln of, when I plug in 0, I'll have ln of 1, but ln of 1 is equal to 0, right? And since I substituted 0 here, I can also substitute 0 on the right-hand side. So I'll have sum of -1 to the n, 3 to the power n plus 1, 0 to the n plus 1, all over n plus 1, plus the arbitrary constant right outside the summation, all right? And what is the value of this guy? So in this case, we're summing up a bunch of zeros. If you're summing up a bunch of numbers that are exactly equal to 0, you'll just get a 0 sum plus c, which is equal to c. So this tells us that c is equal to 0. So therefore, our expansion for ln of 1 plus 3x is exactly the sum of these guys. Because c is equal to 0. All right, and that's it. That's our series expansion for ln of 1 plus 3x. Yes, Kevin, that's the whole point. We take advantage of knowing that the given function g, right? That the given function g is the integral of our function f. But we already found out a series expansion for f. That's why I was allowed to use this. And this series will absolutely converge. And since it will absolutely converge, I can interchange the order of the sum and the integral. And then I'll just evaluate the integral. Now you can do this not only for integrals, but for derivatives as well. So for instance, we are asked to find the series expansion for h of x equals what? Let me see. So if you want to have a series expansion for 9 over 1 plus x squared, 1 plus 3x quantity squared, all right? This is your function. You need to recognize that this guy is related to the derivative of the original function f. So note that the derivative of the function f that we originally had is equal to what? This guy is the same as 1 plus 3x raised to the -1, all right? So this would be -1, 1 plus 3x to the -2 times 3, right? I need to apply the chain rule there. So this would be -3 all over 1 plus 3x quantity squared, right? That's the derivative, which is a little bit different from what we have before, but the nice thing is that they only differ with a constant on top. So now how do I get the given expression? So here, this guy, the function whose power series expansion we are after, is directly related to -3 over 1 plus 3x quantity squared. But to get the 9, I need what? I need to multiply it by -3, right? But I know that this guy, as our solution above, is the expansion, is the derivative of 1 over 1 plus 3x, right? That's what we learned from this differentiation step here. So that means the original series is -3 times the derivative of this guy, but I can replace 1 over 1 plus 3x by its series expansion. Remember, 1 over 1 plus 3x is what? The series expansion we found out from part 1 is this guy. Oh, sorry, I forgot the 3 there. Oh, that's why I had the 3. Sorry, I forgot the 3 here, guys, so let me just insert the 3 here. If I put the 3 there, so there should be a 3 here. So everything's multiplied by 3. So that's how I got the 9 here. Actually, that's my purpose, to have a 9 there. So there's a 9 there. So this is -9. So all we need here is a -1 multiplier. So that means just a negative sign in front of the derivative, right? And this is the derivative of 3 over 1 plus 3x. All right. I don't need a 3 there. Okay. So we found out the derivative, the series expansion for 3 over 1 plus 3x is this. Let me just copy it from above. There we go. We know this expansion to be true. Okay. And this is true for x's whose magnitude is less than 1/3, right? Okay. Now, to find the series expansion for this, it turns out I simply need to evaluate this derivative. But again, this series is absolutely convergent whenever x is less than 1/3. So I can interchange the order of the summation and the derivative. All right. Then when you simplify, so we need to take the derivative. So we need to differentiate this, but luckily only with respect to x. So all those without an x can come out of the derivative. So we just need to differentiate x to the power n. The derivative of x to the power n is just n, x to the power n minus 1. And then the last step is to put this negative sign inside the summation. So we'll have sum from 0 to positive infinity of -1 to the power n plus 1. Again, I had n plus 1 now because there's an extra -1 that comes inside the summation. 3 to the power n plus 1 and x to the n minus 1. All right. So this is how you get the expansion for 9 over 1 plus 3x quantity squared, which turns out to be the derivative of the original function that we had. Oh, Kevin, this is just an additional problem I inserted. So yeah, but I see that for your problem, it's only part until part B. So you don't need to do this derivative, but this is the process if you have the derivative involved. Yes, Christina, you're correct. For part A, for 8A, on Christina's question, you are taking the derivative with respect to x. So everything without an x, everything that doesn't involve the variable x will come out of the derivative. So you only need to differentiate x minus 3 to the power k, right? So, but just be careful integrating make sure you apply all the necessary rules, but I think that's fine. You will have k times x minus 3 to the power k minus 1 there. And also for the integral, everything that doesn't involve the variable x will come out of the integral. Yes, exactly, Kevin. Because with respect to your differentiation and your integration, all the k's are constants, right? Only x are variables. So yeah, you treat them as constants. They come out of the integral and the differentiation operator. Yep. All right, so I hope you will not have a difficult time answering questions 8a and 8b. Is that good, Christina? All right. Okay, any other question for basic power series before we go to the Taylor and Maclaurin series expansions? Oh, probably one last example, so that you won't get surprised if you see this in the exam. Let's call it problem 7. Let's find a series expansion for R10 of x. So, or probably let's do, I'm thinking, should we do R10 of x or R10 of x squared? Let's start with R10 of x. Let's look for a series expansion for R10 of x. Now, I need to notice that R10 is the integral of 1 over 1 plus x squared, all right? Okay, but note that 1 over 1 plus x squared dx will have a geometric series expansion, right? So in this particular case, we'll have a equals 1 and r is equal to, I think, negative x squared, because I can further write this as 1 over 1 minus negative x squared dx, right? And remember that the sum, a over 1 minus r is equal to sum of ar to the n and going from 0 to infinity. This is the sum formula that we know from geometric series, right? Now, the given integrand here looks exactly like a over 1 minus r, with a replaced by 1 and r replaced by negative x squared, right? So the common ratio is negative x squared. So I can write this as the series expansion that I have here on the right using a equals 1 and r is negative x squared, and going from 0 to positive infinity dx. And I know that this will be true whenever the absolute value of the common ratio here is r. Remember, for geometric series, they will converge if the magnitude of r is less than 1. Or you can simplify it by saying that x squared is less than 1. So as long as x squared is less than 1, this series is absolutely convergent. So we can rearrange the summation and the integral. Right? And now I can evaluate this integral first before summing things up, right? So I can actually rewrite it further as this to make it easier to evaluate. I'll play with loss of exponents here. I can split it up into negative 1 to the power n times x to the power 2n dx, right? And I do that so that I don't have that meddling negative sign in front of my x squared, which is right inside the power n, so that I don't need to use substitution to evaluate that integral. And again, this factor is independent of x, so this can come out of the integral symbol. So I'll have this, negative 1 to the power n, and then we'll be left with the integral of x to the power 2n. Remember, n is a constant. So that means this will just be x to the power 2n plus 1 all over 2n plus 1 plus the arbitrary constant c, all the way out of the summation. All right. And this is our expansion for arctan of x, right? Remember, all of them are equal to arctan of x over there. Okay. But we still have an arbitrary constant c here. So the easiest way to check what the value of c is to use x equals 0. When x is equal to 0, we'll have arctan 0 on the left side. On the right-hand side, we'll have negative 1 to the power n, 0 to the 2n plus 1, all over 2n plus 1, and going from 0 to infinity plus c. I just replaced all x's I saw by 0, right? But what is arctan of 0? Arctan of 0 is 0, right? Because tangent of 0 is 0. So, but the right-hand side is just a sum of a bunch of zeros. So that technically will still be 0 plus c. That means this is c. So what we have seen here is that c is equal to all the way back to 0. So therefore, our expansion for arctan will exactly be this guy, because c is equal to 0. All right. Now we can also take advantage of this result to find a series expansion for arctan, say, of x squared. All right. Oh, by the way, this is true whenever x squared is less than 1, right? Now, since we have a series expansion for arctan of x, I can simply replace all x's by x squared in order to get a series expansion. So this guy from problem 7 will give us arctan of x squared. I'll replace all x's I see by x squared. And this should be true for all x squared quantity squared less than 1, right? That's the interval of convergence. Because again, even here in the condition for absolute convergence, I needed to replace all x's by x squared, right? So instead of an x squared, I will have an x squared squared. So you can further simplify this as sum negative 1 to the power n, and going from 0 to positive infinity. This is a power raised to another power, so we multiply the exponent. So this would be x to the power what? 4n plus 2, all over 2n plus 1. And the expansion is valid for all x's such that x to the power 4 is less than 1. Okay. Is that good? So you see here that for these examples, we just relied on the power series for the geometric series expansion, right? But for some functions, they cannot be related, or they are not related to 1 over 1 plus x or 1 over 1 minus x or any similar expressions, right? So that's why we needed a more general way on how to find a series expansion for those more complicated functions. And that's what the Taylor and the Maclaurin series expansions are for. So if you don't have any questions, we'll leave worksheet 19 and go to worksheet 20, which talks about this Taylor series expansion for certain functions. Well, if you have a function f, the series expansion for the function f is of the form summation of f upper k of a over k factorial times x minus a to the power k, k going from 0 to positive infinity. This is what we call the Taylor series expansion about. So this is the Taylor series expansion about x equals a, or around x equals a. Let me change my preposition there. Okay, around x equals a. So let's break this down, this definition down. So what do we have here? So this is fine. You just need to know what the value of A is. A is given in the problem, or if it is not stated, you can just choose x equals zero, A equals 0. That's the most basic choice for A. K's and K factorial here are our mainstays. I guess the most crucial part here is to evaluate this guy. But what is this? F upper K is the kth derivative of F, evaluated at the number A. And that's one thing students forget. They know that they needed to evaluate the derivative of F, but they forget to plug in the value of A, which is the center of the expansion. So this guy should be a constant. So that should not be a function or a variable in your expansion. This guy should turn out to be a constant because you're plugging in the center of expansion. So this would be a constant. Usually we need to take a look at the pattern for the derivatives for that. And then we'll have k factorial as the mainstay there, and x minus a to the power k. Now, a special case is when a is equal to 0. We have what we call the Maclaurin series expansion. So nothing different in the formula except that a is taken to be equal to 0. Okay. Now, here are some formulas that you need to remember. Let's see. So some common expansions. I guess you derived this in class, and you are expected to memorize this bunch. All right. So first is e to the power x. The series expansion for e to the power x is x to the power k over k factorial, k going from 0 to infinity. So it will help a lot if you remember these things. And then from our solutions earlier, we knew that ln of 1 plus x has series expansion -1 to the power k, x to the power k plus 1, all over k plus 1, from 0 to infinity. And these are actually Maclaurin series expansions because you don't see a subtrahend to x, so that means a is equal to 0, which I guess is the most simple type of Taylor expansion. So that's why they are usually used in any application. Cosine will have this form, -1 to the power k over 2k factorial, x to the power 2k, k going from 0 to infinity, while sine will have this expansion, all right. So at least this for series expansion should be memorized, at least for the exam. But I know that's difficult to do for most people, especially for me. I don't like memorization, so yeah. But you can use this as basis for some expansions. So for instance, let's see some examples. So we need to find a series expansion for the following functions around the given value of a. So let's start with this function, x to the fourth, e to the minus 3x squared, around a equals 0. So basically, for number 1, we need to find a Maclaurin series expansion for x to the power 4 times e to the minus 3x squared. By the way, here I am borrowing the examples from Paul Dawkins' notes. I guess I shared the link to his set of notes. They are very good, so you can check them out. All right. So Now what I can do is take note that the first factor is x to the fourth is a polynomial, so I don't need an expansion for that. And for this guy, I can use the expansion for e to the x, right? So, and then just multiply it by x to the fourth to get the expansion for f. So probably you can recall that e to the power x is or has the series expansion x to the power k over k factorial, k going from 0 to infinity, right? So this implies that e to the minus 3x squared will have the following expansion. What's the difference between the left-hand side? So here we have e to the x. Here we got e to the minus 3x squared. So that means we can get a series expansion by replacing all x's I see here by negative 3x squared, right? So let me do that. Replace all x's by minus 3x squared all over k factorial. And that's a valid expansion for e to the minus 3x squared, as long as you are in the interval of convergence. All right. Now I can play with the loss of exponents here to simplify this a bit. So I can write it as negative 1 to the power k, 3 to the power k, x to the 2k over k factorial. All right. So remember that if you're raising a product into a power, each of the factors will get an exponent. So you have a negative 1 here, raised to the power k. There we go. 3 to the power k. There you go. Then x to the 2k to the k. You're raising a power to another power. You simply multiply the exponent. So that's how I got x to the power 2k there, right? And going from, k going from 0 to infinity. All right. So we can use this expansion to get the Taylor series expansion or the Maclaurin series expansion for f of x, which is, what was f of x again? It's x to the fourth times e to the minus 3x squared. So basically x to the fourth can remain there. And then times, instead of this guy, I'll use its series expansion. And I'll just need to multiply them over, right? But in the multiplication, x to the fourth can come inside of the sum. So this would be sum negative 1 to the k, 3 to the power k, and then we have x to the fourth times x to the 2k. So that's just going to be x to the 2k plus 4 all over k factorial, k going from 0 to positive infinity. And that's your series expansion, in particular, a Maclaurin series expansion for the function f. Okay. Everything good with that? So I just want to illustrate that you can take advantage of existing series expansions for certain functions to get the series expansions for more complicated things, right? Or for more complicated functions. Okay, no questions yet? Come on, guys, let me know that you're still there. All good? Okay, so no question because the examples are too easy. Let's try this one then, ln of x. Have you answered this problem in the lecture? Let's say around x equals a equals say 2. Have you derived an expansion for ln x in the lecture? The thing here is that the expansion for ln x would be different from the expansion of ln of 1 plus x. Oh, you already did this, so what do you think? Should I skip this one? Okay, so you already did it centered at x equals 1. So I guess centering it at x equals 2 will be similar. So probably I'll skip this one because you already did this in the lecture, unless you want us to do this, center that x equals 2? Because instead we can try 1 over x squared. Have you tried this one? Okay, so that's good. So we can try this 1 over x squared. But I decided to skip ln x because you already did that in the lecture. So yeah, that will not give us additional insights here. So let's try this one. Okay, so remember the series expansion will look like this. Sum from 0 to infinity of the kth derivative of f evaluated at -1 all over k factorial x minus -1 to the power k. That's the general formula for the for the Taylor series expansion. So this is fine. This will just be x plus 1 raised to the power k. This will just be k factorial. So really, our problem is the kth derivative. So we need to find a pattern or a general formula for the kth derivative evaluated at -1. So let's try that. Let's start with k equals 0. When k equals 0, we get f upper 0 of x, but this is just f of x. So this is what? This is 1 over x squared. So this means f upper 0 evaluated at -1 will just be equal to 1, right? Now when k is equal to 1, we'll have f upper 1 of x, which is just the derivative of this guy, but its derivative would be what? Its derivative would be, this guy is x to the minus 2, so the derivative would be -2 times x to the minus 3, right? So that means the first derivative evaluated at -1 will just be -2 over -1 cubed. So that would be what? +2. All right. Kindly double check my arithmetic here because we want to get the correct pattern. So I hope you will check it. What happens when k is equal to 2? When k is equal to 2, the second derivative will be 6, or maybe I should write it as -2 times -3 x to the minus 4, right? So when I plug in -1, I'll get -2 times -3 all over -1 to the 4th. So this will just be -2 times -3. Or I can write it as -1 to the power 2 times 3 times 2, right? I don't want to multiply because I'm trying to get the pattern. Is the pattern now obvious? If not, then we can take another derivative. When k is equal to 3, we get f upper 3 evaluated at x will just be -2 times -3 times -4 x to the minus 5. All right. So this tells us that the third derivative evaluated at -1 will just be what? This will just be -2 times -3 times -4 over -1 to the 5th power. All right. So this will just be what? -1 cubed all over, -1 cubed times 4 times 3 times 2 all over -1 to the 5th. Maybe I should have written -1 to the 4th here so that we see the pattern, -1 to the 3rd. All right. Now I guess we're ready to take the pattern. So f upper k evaluated at -1 will be what? Well, let's start with the numerator. Well, in the numerator, we have -1 to the power 3 for the third derivative, negative 1 to the power 2 for the second derivative, negative negative 1. Yeah, I forgot the negative here. Negative 1 to the power 1 for the first derivative, so Kevin is correct. We'll have negative 1 to the power k on top. And then what happens to the constants here? For the third derivative, I have 4 times 3 times 2. For the second derivative, I have 3 times 2. For the first, I have 2. Well, close enough. Close enough to k factorial. But for the third derivative, we're doing 4 factorial. For the second derivative, we're doing 3 factorial. So what we have here would be k plus 1 factorial. Good. And that's why I did not multiply things out, because I want to see the pattern, right? And true enough, when k is 3, I have 4 factorial. When k is 2, I have 3 factorial. So it's always one step ahead for the factorials. All right. So that's why we have k plus 1 factorial there. All over, we have a negative 1 to the power what? When k is 3, we have to the power 5. When k is 2, we have to the power 4. When k is 1, we have power 3. When k is 0, we get, you can think of it as negative 1 to the power 2. Okay, good. That's going to be negative 1 to the power k plus 2. I think, Kevin, your first answer was correct. Because you have k equals 3, so you have 5 there, right? And actually, we can simplify this. We can say, oh, this guy can be canceled by this. So I'll have k plus 1 quantity factorial all over negative 1 squared. But what is negative 1 squared? Negative 1 squared will simply be positive. So this is just k plus 1 factorial, right? Yeah, I think that's what will happen. And just be careful with the first case when k is equal to 0. See if this formula holds, because otherwise you need to separate what happens when k equals 0. Having k equals 0 is tricky. Let's see if this formula works for k equals 0. When k equals 0, this should be 1 factorial. But what is 1 factorial? 1 factorial is just 1, and luckily that fits in the formula. If that didn't separate k equals 0 and not include it in the general formula for the summation. All right. So here we'll have what? So we now know that 1 over x squared will be equal to the sum of what? Of this guy. Let me just copy this to serve as my pattern here. Okay. Right. Oh, we already know how this looks like. F to the upper k at negative 1 is just k plus 1 factorial. So copy that over. And then over k factorial. Where did that k factorial come from? That came from the formula, right? There's an over k factorial. And then this guy simplifies to x plus 1 to the power k. K goes from 0 to positive infinity. And then here we can further simplify. Remember that k plus 1 factorial all over k factorial will only leave us with a k plus 1 left in the numerator. So essentially the simplified expansion for 1 over x squared will just be k plus 1 times x plus 1 all over k, k going from 0 to infinity. Okay, and the interval of convergence here can be obtained by using the, I think using the ratio test. All right. Any questions with this? Okay, I hope the basics make sense so you can try it on your own. Again, the crucial thing here is to find a pattern for the derivative. And again, the derivative should be evaluated at the center of expansion. So this guy will always be a constant. No variables should appear here, right? So no x's will be there because you're plugging in x equals a, all right? Then you can do the simplifications, you get this, but this will be only valid for some values of x, right? And you can do that by using the root test to find the interval of convergence. Okay. All right, so do you guys have any questions? Because we already passed time. So any questions? How do you feel about the topic? Is it easy or you're still getting there? Okay, you don't want to disclose your status. Okay. Yeah, clearer than the series test because, yeah, Kevin, you're correct. Because there's only a uniform way of how to do this, right? There's a single process, but for testing series for convergence, it's quite difficult because you have to choose what type of test to apply. And I think that's the most difficult part there. The challenging part here at this point is to determine what are the appropriate or what is the pattern for the kth derivative of your function evaluated at the center of the expansion. All right. So what we'll do on Friday is probably take a look at some more examples of Taylor series expansions. Maybe I'll pick some problems from this worksheet and let me see if some will be interesting. All right. And I guess I encountered a lot of students who asked me about the Taylor series expansion. They need to find p sub 2n of hyperbolic cosine of say 6x from the quiz. I don't know if you have encountered this already. So yeah, I was expecting somebody to ask me this, but perhaps you haven't had a chance to take a look at it yet. But okay, we can talk about this on Friday. All right. So if there are no questions, then let's call it a day. Thank you for coming, and then let's see each other again on Friday. See you then, guys.